Alright, so now we can continue with these two functional groups by looking at some of their properties. And the dominant feature, the most important feature of a carbonyl is this highly polarized carbon-oxygen double bond. And so what this results in is a strong dipole and allows for dipole-dipole attractions between different carbonyls. Now, this ends up being a somewhat strong attraction, but because there's no hydrogen on that carbonyl, it's not nearly as strong an attraction as we see with hydrogen bonding. And so if we add aldehydes and ketones into our sort of group of functional groups, we'll see that they fall somewhere in the middle. So recall at one end, we had the very nonpolar alkanes, which only have van der Waals forces, and therefore very low boiling points. At the higher end, and we're making all of these similar by molecular weight, we had the alcohol, which has a much higher boiling point, 117 degrees. So what about the aldehyde and ketone? Well, first, they have very, very similar attraction. They're both dipole-dipole, and with the same number of carbons and the same effect. In what I've drawn here, the two molecules are roughly the same shape, and so the effects are going to end up being similar. And so in this case, for the aldehyde, we get a boiling point of 76 degrees Celsius and 80 for the ketone. And again, this is based on van der Waals being the primary attraction, primary intermolecular force for the hydrocarbon, dipole-dipole for the aldehyde and ketone, and hydrogen bonding for the alcohol. Now, what about water solubility? Again, due to the presence of the oxygen, we see a lot of the same patterns that we saw with alcohols. So low molecular weight alcohols are generally very soluble in water, or completely soluble in water, whereas much higher molecular weight alcohols are pretty much completely insoluble in water. And the same thing is true for ketones and aldehydes. Low molecular weight ketones, for example acetone, highly water soluble. But when we get to higher molecular weight, typically anything above 4 or 5 carbons, those ketones and aldehydes typically end up being either sparingly soluble or, in most cases, completely insoluble. Now, carbonyls have another important property, and it's one we're just going to mention briefly, but I think it's important to mention. In general, for most organic compounds, CH bonds are not acidic. But in carbonyls, we refer to the carbons next to the carbonyl as the alpha carbons. And the alpha carbons, turns out, are unusually acidic for a CH bond, with a pKa of about 18. And while this might not seem that acidic, and it isn't compared to something like hydrochloric acid, this is actually very similar to an alcohol. And the reason for this acidity is because it's next to the carbonyl. We're not going to get too much into that, but when we deprotonate, and it could be either one of those carbons, we end up with this negative charge. Well, remember, the carbonyl itself is a dipole, delta plus on carbon, delta minus on oxygen. So this negative charge is stabilized by the fact it has a strong dipole as well as a double bond next to it.